We're going to continue today on chapter 2. We're talking about, we just started section 2.3, which is called the algebraic and order limit theorems. So let me quickly remind you what this is about. And we're, of course, are going to use the definition of limit of a sequence that we developed the previous class to talk about useful properties of limits, okay? And this is important because, as we saw when we introduced the chapter, weird things can happen if one is not careful about how you can define when something approaches infinity. So let me switch to the page. This is where we started last time. We said what it means for a sequence to be bounded, right? So bounded means there is some positive real number which has the property that our sequence, every xn in our sequence, is going to fall between -m and m. Everyone will be between these two numbers, right? Or remember this inequality. Any inequality with absolute value that has less than or equal, you can restate it as follows. Right? It means that the number here is between -m and m. And that's what we have right here, right? Or the way we like to say it with distances, this is the distance to 0. The distance from 0 to xn is at most m. So here's 0. And if you measure the distance from 0 to xn, whether it's to the right or to the left, that distance is at most m. We provided a couple of examples, like this sequence is bounded, obviously. You can use m equals 1. This one is unbounded, clearly, because by the Archimedean principle, we can find a natural number as big as we want. So it would exceed any real number m that you give me. And then we stated this theorem and sort of argued why it was true, but we're going to write it now today in a convincing way. And it says that every convergent sequence is bounded. And this is the picture that went with the idea of the proof. The idea of the proof was to imagine that the sequence converges to this number a. Choose a neighborhood around a. It really doesn't matter how big you choose it. I'm choosing of 1 just because I like the number 1, but you can pick whatever you want. And then because the sequence is convergent, we know that eventually all the elements of the sequence are in here. And by eventually, I mean all of them, except a few renegades is what I was calling them last class, which is the ones that I drew over here, right? So that's the idea of the proof. We're going to use that bound and then bound individually the finitely many that may be outside. So here we go, proof. Suppose that our sequence xn converges to the number a. Then, using epsilon equals 1, there is some capital N, a natural number, such that for every little n bigger than capital N, xn minus a is less than epsilon, but we chose 1 as our epsilon, right? Or you can rephrase this in the following way. If n is bigger than capital N, then xn belongs to the one neighborhood around A, right? So that you can combine this idea with the picture. So the picture says that all the numbers will be here after capital N. Remember that capital N is our entry point. So once you exceed capital N, bam, all the elements of the sequence are going to be in here. They're going to be within 1 unit of A. All right? Okay, so that tells me that I can now combine, I can now control. I mean, remember what I want. I want to show that my sequence is bounded. So what I want to show is that the absolute value of xn is bounded by some number. Okay? And we can do that. Right? And this is a neat trick that will happen many, many times. So we may as well introduce it right now. So what we really want to bound is the absolute value of xn. So note that this happens. If you want to, whatever you want to bound, if you're using something auxiliary to do it, you should introduce that auxiliary part that you want to use. In this case, I want to use this inequality, xn minus a less than 1 in absolute value. So that's my trick. I'm going to put it here. I'm going to put xn minus a. Then, of course, to make this right, I better, if I subtracted a, I better add it so that things are copacetic, right? I mean, we don't want to write something here that is not true, but this is definitely true. Adding and subtracting something is fine, right? It's like putting a 0. And then the trick here is to use the very useful triangle inequality, right? So we know that if we have the absolute value of a sum, we can bound it. This is the triangle inequality. Triangle inequality. We can bound it as the sum of the first term plus the sum of the second term. And that's awesome because now I can use my inequality that I had here from before. I knew that this quantity over here is bounded by 1. So this is less than 1 plus absolute value of a, right? So I don't know if you realize, but I have almost solved the problem already because I can now control all the xn's that are bigger than n. So maybe I should add it here so that it's clear. Not that if little n is bigger than capital N, then this happens, what we just wrote here, right? Because this is the same as that. By triangle inequality, this is true. And then because n is bigger than capital N, I can use this inequality on top, and that's why I get now a 1 here, okay? So we're almost done. We would be done. We could call this capital M if, let me go back to the picture, if there were no renegades, if we had catch already everyone. But maybe there are a few guys over here outside. So now we need to get to control those as well. And that's easy. This is the way we're going to do it now. Look how convincing this part of the argument I expect will be. So let M be the largest. So we're going to pick the maximum of the following numbers. Absolute value of x1, absolute value of x2, all the way to absolute value of x capital N minus 1. Those are the possible renegades. And then I'm going to add this number, 1 plus capital A. And then I claim this capital M works. First of all, I'm going to convince you that this is a good definition, that I'm not defining something that is maybe infinity. And this is good because this is a finite list, right? This is important. I don't know what the capital N is. Maybe it's gigantic. Maybe it's a million. But that's okay. That means I have a million minus 1 numbers here, 999,999, which I can look for the largest one, and then also add this into the mix, right? And pick the largest one. That will be this capital M, okay? And then I claim this capital M works. Why would it work? Well, because, so I'm just, I could just finish the proof here and say that it works, but I'm just going to add a sentence. So indeed, if note that xn in absolute value, or let me call it xm, the following happens. So it has two possibilities. This is going to be less than or equal, well, itself, if m is less than or equal n minus 1. So if it's one of the first few, I'm just going to use itself. And if it's not one of the first few, then I can use my inequality right here on top. It means the little m is bigger than capital N, and then it's bounded by 1 plus a. Right? So you should believe this is true. So if I have a little index, it's of course less than or equal than itself. And if I have a big index, then I can use the inequality we had before, which is 1 plus a. And then in either of the two cases, either of these two is less than m, right? Because this one is less than the maximum, and the maximum includes that number. And this number is also a member of this collection of elements, so the maximum, of course, beats it. So we are done, right? This number xm is less than or equal m, no matter what the index is. So our sequence xm or xn is bounded. Okay, and that's the end of our proof. Every convergent sequence is bounded. Okay, questions so far?
For the inequality for 1 plus absolute value of A, could you also do n is greater than n plus 1 or n minus 1? Excuse me.
You mean this one here for m?
Yes.
I didn't.
Could you say m is greater than n minus 1?
This little m?
Yeah.
Yeah, okay, I see what you're saying. Yes. So you're saying, can we change this to m greater than n minus 1?
Correct.
Yeah, they're the same. When you're talking with integers, you can say x greater than or equal 4, right? Or you can say x greater than 3, and both of them say the same thing if we're talking integers, right?
All right.
Yeah. Good. So next one is actually very important, and we're going to use this, and we're going to take our time to do this one correctly. So this is a so-called algebraic limit theorem in our book. And it says the following. It says that if we denote by A the limit of an and by B the limit of the Bn, notice this is implicitly saying that an is convergent and Bn is convergent, and their corresponding limits are A and B. Then the following happens. It has 4 parts. Part 1, if you do the limit of C times an, you get Ca, where C is any constant. So in other words, if you do the limit of a constant times a sequence, you're allowed to take the constant out. That's what it says. Property 2, if you do the limit of this other sequence, which is the sum of an and bn, so we create a new sequence, which is the sum of the other 2 sequences we had before, then this will be convergent, and the answer to that limit will be a plus b. Informally, we like to say this property as the limit of a sum is the sum of the limits, right? We can interchange limit and sum as we see fit. Property 3, similar thing happens with multiplication. If you multiply an and bn, you get something convergent, and the answer to that is the limit of the a's times the limit of the b's. So a times b. Again, what this means is the limit of a product is the product of the limits. And property 4, quotients work too, with a little bit of care, meaning this sequence will be convergent, and it will be convergent to the limit of the an's divided by the limit of the bn's, provided b is not 0. Provided you don't divide by 0, right? Otherwise, the expression on the right is undefined. Okay? So those nice properties you know about limits of sequences are true, in other words, right? So you can do the limit of a sum by interchanging the order of operations, the same with product and quotients and multiplication by constants. Good. So let's get to it, and we're gonna prove them all, and we're gonna more importantly explain how is it that you could prove things like this, right? What is the general technique that you should follow, all right? Now remember, we sort of always have a discovery phase here, right? To prove that a limit is anything, you need to find out, like we stated last class, for every epsilon, you need to find out the capital N that is gonna make this work, right? Find out the entry point. So usually you start from the last part that you want. Yes? So I'm going to start with number 1. What is it that we want? We want, so to show, let me write it like this, to show limit of CAN equals CA, we need to do the following. Given some epsilon greater than 0 that someone tells us, we need to find capital N, some natural number, such that if little n is bigger than capital N, then the element in our sequence is close to the limit at distance of epsilon. It's epsilon close to CA, or alternatively, this CAN belongs to the epsilon neighborhood centered at CA. That's an alternative way of saying the same thing. So that's what we need to do, okay? So this is not part of a proof, by the way, right? This is, I'm just telling you what we need to do, okay? And we actually have some help. We already know, let's go back, don't forget our assumptions. So we do have some assumptions here, namely these ones over here. Right now, we're only going to use the A's, but we do know that the limit of the ANs equals A. So we already know a similar property like this works if you use AN and A instead of CAN and CA. So we better use that at some point. Okay, so as usual, so in fact, let me write that down. We do know that for a given, let me give it a different name so we don't confuse ourselves. For a given epsilon prime, there is n prime such that if n is bigger than n prime, then AN minus A is less than epsilon prime, right? So we do know this because this is exactly the definition of the limit of AN being equal to A, okay? So this is precisely limit of AN equals A. That's the meaning of this, okay? So then, still as part of our discovery process, what we want to do is start from what we want. See, and let me tell you the informal way in which you should think about things here. See, the informal way in which you should think about this is you can control AN minus A. We do have control. If we get AN minus A, we can control that. We can make it tiny, right? We can make it as small as we want by picking n sufficiently large. So we do have control of these. And what we want to do is have control over this one over here. So the main idea of all of these proofs is to try to tie the thing you want with the thing you know, right? So how can we gain control over this one if we know control over the bottom one? So, and like I said, the discovery part works as follows. You start from the top one, and you say, okay, we want CAN minus CA to be less than epsilon. How can I relate this to that one? And this is actually one of the easiest ones, the one we have currently. Clearly, you can see that you can maybe factor the C, right? So this is equivalent. This one over here is equivalent as if I take the C out in absolute value. So I factor it. Let me go step by step. So that's the same as doing this. C times AN minus A less than epsilon, which is the same as simply taking the C out in absolute value. Right? Okay. And this one makes us happy because we can control this one. Remember, we finally brought to our attention the one we can control. It's right here, AN minus A. That should make you happy, right? When you get something like this, you're on the right track. So the only thing you need to match now is what kind of epsilon prime do I need so that the one we are given implies this one, right? Because remember, we're thinking about things backwards. This should be the last step. So to get to this step, we should come from this one. And to get to this one, we should come from this one. So, and then this one finally ties it to what we know. So what we need to think is, what epsilon prime should we use to make this work? All right? And, all right. So what do you think? What should be our epsilon prime? Anyone?
Epsilon prime times the absolute value C. I'm trying to figure out if it's times or divided by. Like I'm not sure how we would get there.
Right. It should be times, right? See, if you start over here,
that's what I was thinking.
Or let's see, or is it divided by? So you want this one to imply that one. So if we make it times, it's actually divided by, right? Actually, I think you were right.
Okay.
Which brings a little problem, right? What if we're dividing by 0? But let's forget about that for a moment. Let's suppose that C is not 0. So it seems like epsilon divided by the absolute value of C should work, right? Because then if you put it in here, seems to work. Let me put it. Right? Because then if I start with that one here, if I simply multiply, see, let me write here, it would be like this. Epsilon prime, but epsilon prime, we're saying it's going to be this one. So then we can multiply by C and get the one we want, right? So it seems like this one implies that one. And now I think we have a plan, right? Of course, this plan is only going to work out if C is not 0. So I'm going to leave the 0 case for you guys later on. It's actually, well, we'll do the 0 case later. Let's not leave it. We'll do it later, okay? So is that clear that we have a plan now of how to write the proof? So the way to write the proof is we're going to start with an arbitrary epsilon. So somebody gives us an epsilon. We create this epsilon prime. We use this epsilon prime in the definition of the limit of an equals a. And that is going to give us this inequality. We change that epsilon prime to epsilon. We'll multiply by absolute value of C. That way we get this one. And this one is the same as that one. And that one is the one we want. Okay? That's the plan. So now we just need to write it down, right? We essentially are done. We just need to write down our proof in the correct way. So here we go. So here is the real write-up of the proof. So,
Professor,
yes?
you could draw like a picture of like what we want to do.
Not really. For this one, not quite. I mean, I can try. So, I mean, intuitively, this should be, okay, let me try to draw a picture with a specific constant. So here is what we're trying to do. Actually, I can draw a picture. Here is what we have to do. So I'm drawing two real lines, and somewhere over here is A. And let me use, so let's put 0 here, just to give you a way of visualizing. And for this picture, I'm going to use C equals 2. All right? So we have a sequence that converges to A. Let me draw it. So there is some sequence here, AN. I don't know where it is. Maybe A1, A2, A3, and then maybe A4 jumps on the other side, and then A5, and then A6, 7, 8, 9, It converges to A, right? And then what we're now considering is a new sequence, which is twice the original one. So this number 2A1 is going to be all the way over here. Let me make my picture. This number A1 is going to be now over here. It's 2A1. And then A2 will be more or less over here, 2A2, and then 2A3, and then 2A is here. And what you should realize is that my picture sort of is going to look the same, but magnified by a factor of 2, right? So these numbers are still getting closer and closer to 2A. Yeah? And that's exactly what we're trying to do here. So in our definition of limit of the AN is telling us the following. It's telling us if you want to get within epsilon, so if you pick an epsilon here, an epsilon prime, I can tell you a capital N prime such that if your index is bigger than that capital N prime, then everyone will lie in here. Yes? And now the thing is how to use that information to do it for this one. And we just sort of discovered how. The way it's going to be is like follows. You pick an epsilon here, some epsilon around 2a, and you want to use that epsilon to have a corresponding statement over here. And to go from this picture to that picture, what do we do? To go from the bottom to the top one.
You divide.
Yeah, you divide by 2, right? So look at here, 2a goes to a, and 2a1 goes to a1. So from here to here, you divide by 2. So that's exactly what we're doing here. Notice we're taking epsilon and we're dividing by the absolute value of c. Right now, I'm doing the easier case because I picked a positive number. If the number that we're using is negative, the picture is a bit more confusing because you not only magnify or dilate, you also flip it, right? When you multiply by a negative number, everyone goes to the other side. You flip it. But other than that, that's exactly what we're doing. We're going to use epsilon over 2 to create our picture here, and then hopefully that will make it work for this case over here. All right? And we just verified already our inequalities seem that they're going to work. So let's do the write-up. So here's the write-up, the proper write-up once you discover what is the epsilon prime you should use. And that epsilon prime gives you the n that you need to use. So here is the proof. Proof. You always start picking an epsilon, right? So let epsilon greater than 0 be arbitrary. That's always the first line. Set epsilon prime to be, well, okay, we're doing the case, assume C is not 0. We'll do the 0 case later, all right? So set epsilon prime to be epsilon over the absolute value of C. Because the limit of the ANs equals A, then using epsilon prime, we know there is n prime, a natural number, such that if little n is bigger than n prime, then an minus a is less than epsilon prime. That's the definition of limit of an equals a using a very specific epsilon. We're using epsilon prime, which is this guy, right? Epsilon over absolute value of C. Okay, and then we say the following. So let capital N be n prime. So the n we're looking for is actually the same one, n prime. And then let's verify that it works. How do we verify it works? Suppose that n is bigger than n prime, than n. Well, this is the same. Capital N or n prime, they're the same. Capital N, which is n prime. Then we can use this inequality and we can multiply it by absolute value of C. So this is what we're going to do. We're going to write down our first line from the discovery, which is then this happens. CAN minus CA is the same as C parentheses AN minus A, which is the same as C times AN minus A, which now we're going to use our inequality, this inequality, which is less than epsilon over absolute value of C. These guys go away, and we get just epsilon. And we're done, right? Let me check why we're done. What is it that we did? Given an epsilon, We found a capital N that in this case happened to be the same as the capital N prime. Okay, fine, it was the same. And then what happened? Well, if you pick a little n bigger than that capital N, this inequality works, the one that we had here, and we could use it here to get that CAN minus CA in absolute value is less than epsilon. So we are done. So we are done. This means that i.e. the limit of CAN is CA. All right? Oh, we're done in the case where C is not 0. What about if C is 0? Well, that case is super easy, right? Because if C is 0, then what is the sequence CAN? Let me just write a little sentence. If C is 0, then the sequence CAN is just the sequence 0, right? It's a constant sequence, 0, 0, 0, 0, 0, 0, all the time 0. And of course, that sequence, a constant sequence, is convergent because it's 0 all the time, and it converges to 0. Clearly, the limit of 0 is 0. So we are done in that case as well. So it works because 0 is 0 times A, right? So it works regardless. It's in fact an even easier case. Okay? All right. If you're still having, I mean, if this is the first time you've seen proofs like this, I understand that I mean, it's going to take a little bit of time to get used to them, right? And of course, like I'm always telling you, practice, 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 practice. I mean, you can see me do it 100 times, but it's not going to be until you do it on your own and you struggle and you have a hard time, but you finally figure it out that you will be able to succeed, okay? So let's get to the second part. So the second part is now about the sum. So item 2. So this time we want to show, so we want the limit of AN plus BN to be A plus B. So again, the discovery part would be to start from the last part. So the last part is, given epsilon greater than 0, find capital N such that this sequence, AN plus BN, minus the purported limit, which is A plus B, is less than epsilon. Can we make this happen is what we want, right? And this is what we want. And now, what do we know? Let's write what we know. We know, given, let me give the different names, epsilon 1 and epsilon 2, there are N1 and N2 natural numbers. I'm doing 2 because we have the limit of the A's and the limit of the B's. So given this, there are those such that, oh, I didn't say here, whenever little n is bigger than capital N. Such that, so there are, this happens so that AN minus A is less than epsilon 1 whenever little n1 is bigger than capital N1, and Bn minus B is less than epsilon 2 whenever N2 is bigger than capital N2. This is what we know, right? So then our task is to see if we can relate the one we want with the ones we can control, right? So how can we make this one look like this in some sense? Okay, and obviously the first thing you can do here on the one we want is to combine like terms, right? Put the A's together with the A's and the B's with the B's, right? So then we want, let me write it again here, we want AN minus A plus BN minus B. That's what happens when you put them in the order, the A's first, the B's later, right? And then how to relate these to these other two? Well, again, our old friend, the triangle inequality, is helpful here, right? When you want to break down the absolute value of a sum into the sum of the absolute values, it's not equality, but you get one of the inequalities, right? The inequality in this direction, you get It's the triangle inequality. Let me just picture a triangle here to explain to you where it comes from. So this is true. It is true that this is overestimated by the sum of these two. And that's exactly what we need, because we can control this one and we can control that one. We control this one using epsilon-1, and we can control that one using epsilon-2. Okay, so we're done. I think we got it. All we need to do now is specify what are those epsilon-1s and epsilons-2, and figure out what is going to be the n that is going to make it all work. Okay, so to begin with, what epsilon-1 and epsilon-2 should we use? Well, when we tag these inequalities here, these are going to be epsilon-1 plus epsilon-2, right? When we tag them over here. But that's not what we want. We want epsilon. So we want this to be epsilon. So that's what we need to do. We need to pick epsilon-1 and epsilon-2 so that when we add them together, we get epsilon. And you have choices here. There's tons of ways of doing this. But people usually go for the easier, the more natural, which is maybe let's make them half and half, right? Let's make this half of epsilon and this half of epsilon so that together they make a whole epsilon. But there's no reason why it has to be half and half. You can maybe go 1/3 and 2/3 or whatever other division you want. It doesn't need to be equitable here. But why not? That seems like the simpler thing, right? So epsilon-1 equals epsilon-2 equals epsilon over 2 should work. Okay, and let's see if we can do it. Okay, and also, what is the capital N we're going to need to use? We're going to discover that at the same time as we write the proof. Okay, so here is now the proof. So all of this was the discovery, the part you need to do to figure it out. But now here comes the proof. Proof. We always start the same way. Let epsilon greater than 0 be arbitrary. Now I'm going to set epsilon-1 and epsilon-2 as epsilon over 2. Then, because the limit of an equals a and the limit of bn equals b, then, and here in parentheses, using epsilon-1 for an and epsilon-2 for the sequence bn, there are n1 and n2 natural numbers such that if n is bigger than n1, greater than or equal, then an minus a is less than epsilon-1. Remember that this is epsilon over 2. And if n is bigger than capital N2, then bn minus b is less than epsilon-2, which is epsilon over 2. Right? Okay. All right. Now, what should be our capital N? That's the last piece of the puzzle here. What should we pick as our capital N? Now, remember, we need to pick it in a way that we can use both of these simultaneously, right? So we need to pick it in such a way that if the little n is bigger than the capital N we need to choose, both of these will work. So what capital N should we use?
Maximum?
Yeah, the largest of the two, right? If we pick them, the largest of the two, then it will work for both. Exactly. So set capital N to be the maximum of N1 and N2, right? Pick the largest of the two. And if you pick the largest of the two, then when you have a little n that is bigger than capital N, it will satisfy both of these. If little n is greater than or equal capital N, then little n is bigger than capital N1 and little n is bigger than capital N2, right? Because little n is bigger than the largest. So in particular, it is bigger than both. then by the previous two inequalities, the following happens. Thus, an minus a is less than epsilon over 2, and bn minus b is less than epsilon over 2. Finally, and that's the last step, if we write an plus bn minus a plus b, that's the same as if we change the order. I'm sort of rewriting my discovery phase. If you look at it, this is the same. I just rewrote the order. Then this is the triangle inequality, and now I'm going to use my two inequalities that are in the line right above. So this is less than epsilon over 2 plus epsilon over 2, which together make epsilon. And we're done, right? We are done. Let's review. What did we do? We started with an arbitrary epsilon right here. Without epsilon, we constructed epsilon 1 and epsilon 2. With those epsilons 1s and epsilons 2, we know there are capital N1 and capital N2 that make this work. With those capital N1 and N2, we created capital N. And we did it in such a way that if little n is bigger than capital N, then little n is bigger than the two n's, which means I can use these two inequalities, and I'm going to use them right here when I add these two together, right? Write this, use the triangle inequality, add them together, use the inequalities we use from the previous limits, and I get epsilon halves plus epsilon halves equals epsilon. So I just got it, right? The sequence an plus bn is within epsilon of a plus b. We are done. The limit of an plus bn equals a plus b. All right? Questions? Okay. Now, so far, I admit it. I mean, if maybe those of you that never seen it, I'm glad, because now I am actually explaining it with a lot of detail. Those of you that have seen arguments like this or that got it right away, then maybe are getting a little bit bored. Like, Professor, this is not that bad. I mean, you just, it seemed like you're over-explaining. Well, a little bit, because it gets more complicated, right? So let's try the product one, right? The product one and the quotient one will be considerably harder than the one we just did. Okay, so number 3. So for number 3, now we want to look at the product. So we want the limit of an times bn to be ab. So this is what we want. We want given an epsilon, to find capital N such that an bn minus ab is less than epsilon whenever little n is bigger than capital N. That's what we want. And what we know is the two previous ones that we wrote before. We can again use epsilon 1 and epsilon 2. So we know that given epsilon 1, epsilon 2, there are n1, n2, such that an minus a less than epsilon 1 whenever n greater than n1, and bn minus b less than epsilon 2 whenever n is greater than or equal to n2. And now the complicated thing is that it's not as easy as before, right? We cannot simply multiply these two to get that one, kind of like we did with the sum. For the sum, it was kind of easy, right? It was like, oh yeah, I mean, we can add up, we still have it here. We add these two together, we somehow get the one we want. It's not exactly equality, but we get the right inequality, right? To relate these two. But here, something like that doesn't work, right? You cannot just, if you multiply these two, you're not gonna get that one. Remember, when you multiply things here, you foil it, right? You're gonna get 4 terms. you're going to get AN and BN, and negative A times negative B will be positive AB. And we don't have positive over here. We have negative. So that's going to be a problem. Plus, you get the other terms, negative A with BN and AN with B. So it's a bit more complicated than the other cases, right? We need an additional idea, an additional trick. And in this case, the idea is to look for a middleman, all right? So again, we start with what we want. So let me put it here. We want AN, BN minus AB to be less than epsilon. And again, I think for the moment, I think I'm gonna assume that A is not 0. If A is 0, then if capital A is 0, then well, we'll do that case separately. I think it's, in fact, it may be one of your homework problems to deal with that case. So we're going to assume A is not 0. You'll see in a moment why. And we're going to introduce a middleman here to work out this expression of what we want. Okay, here's how we're going to do it. So I'm going to put this and then minus AB. And over here, I'm going to add and subtract something that will be useful to us. And it will be this. I'm going to subtract ABN and then add it, ABN. Okay. If you think about it, it's kind of like trying to look for a middleman. So this ANBN has to, the sequence multiply with itself. Whereas this one over here has a constant, because A is a constant, with an element of the sequence. And the last one has just 2 constants. So this is the way of looking for a middleman, right? Looking for half constant, half sequence. Negative AN, BN with ABN. And the reason this is useful is because we can then combine the first 2 with the last 2, right? Look at it here. If I combine the first 2, they have in common BN. So it looks like AN minus A times BN. And the last 2 have in common A. So that's A times BN minus B. And then I can use the triangle inequality. So from here, if I use the triangle inequality, this will be less than or equal AN minus A parentheses BN plus A times parentheses BN minus B, right? And then even more, I mean, the absolute value of a product is a product of the absolute values. That was an all homework in chapter 1. So this is actually the same as AN minus A quantity BN plus A times BN minus B. Okay, and now we are getting somewhere. Why? Because we want to control this expression over here, the AN BN minus AB. And we now have that is bounded above, so it's smaller than the sum of these 2. And then we ask ourselves, can we control these 2? And the answer is yes. This one we can control because we can get BN minus B to be small, right? So we can ask for these to be small. See, right here on top, it says we can make it smaller than epsilon 2. And we can pick epsilon 2 to be whatever we want, right? So what epsilon 2 should we pick? Well, we can pick something so that this one becomes, again, remember, we're going to add 2 things here. So maybe it makes sense, again, to try to make it so that this is less than epsilon halves plus epsilon halves. That's what we want. So remember, I haven't proved this, okay? This is my want. And to do that, maybe we want this to be at most epsilon over 2 and that to be at most epsilon over 2. So to control this part over here, we can do it the same as with the previous problem, the first one. We can simply divide by the absolute value of A over here, right? So pick epsilon 2. So to deal with this one, pick epsilon 2 to be epsilon over 2 absolute value of A. That should work. However, on the right one, we have another problem, right? For the right one, you may be thinking the same way. You'll be, okay, professor, yeah, I got it. I got it from here. Now you did this one, let me do the other one. So for the other one, now I can control the AN minus A. So I go right here on top and I can use whatever epsilon-1 you want. So why don't I pick over here, let me use a different color. I come over here and I say, let's pick epsilon-1 to be epsilon over 2 times Bn. Okay, and then it will work. And however, this is wrong. Why is it wrong?
Because Bn is a sequence.
Yeah, I mean, this is changing, right? My epsilon should not depend on anything other than constants, right? So this one is fine because I'm using capital A, and capital A is some number, right? And now you see why I need it to be non-zero, because I'm dividing by it. So that's the reason we want it to be non-zero, and we'll do the zero case later. But here, this is not a constant. This is changing. So to make it work, we need to consider the worst case scenario, right? So we're dividing by this. What would be the worst case scenario? The worst case scenario would be when this number is as big as possible, right? The bigger the Bn, the more problems I have. Because if the Bn is gigantic, then it forces me to pick something smaller and smaller and smaller, right? Remember, my epsilon-1 has to be greater than 0. So if the Bn is a sequence that goes to infinity, I'm in trouble. If the Bn is a sequence that goes to infinity, I cannot do it because this can be as small as you want, right? This can be as close to 0 as you want. And I cannot make it close. I cannot pick 0. I need to pick something greater than 0. So let me ask you then the following. Is it possible that the Bn goes to infinity? Could that happen? No.
We just proved that it has a limit, and anything that has a limit that exists bounded.
Yes, thank you, Aim. That's exactly right. Now we're going back to the first thing we proved today, right? The first thing we proved today is if something is convergent, then it's bounded. So this guy is convergent, therefore it's bounded. So then perhaps we can use the bound instead of Bn here, right? So to consider the worst case, we can use the bound M of the sequence Bn instead of Bn here, right? So then the way to fix it, so this would be wrong. Let me cross it. So if you pick this one, I'm gonna, and by the way, this error happens a lot. I've seen it, I mean, I've taught this class now this is the fourth time. And I have always students that pick an epsilon that depends on the sequence, right? So make a mental note to check. In fact, let me write it here. So like a warning type thing. So your epsilon cannot depend on a sequence, right? Very important. So don't choose it like this because it's wrong. So the way to fix it is to pick epsilon-1. So the fix, and you see why it's going to work, is to pick epsilon-1 to be epsilon over 2m, where m is the bound of the sequence, Bn. Okay? All right. And if we do all of that, it seems like it's going to work. So, and again, we need to find a capital N that where you simultaneously can work one and the other. So it again will be a thing where you pick the largest of N1 and N2 kind of thing. Okay? But I think we're ready to write the proof. So let's see if we can do it. Proof. So we start with an arbitrary epsilon. let epsilon be greater than 0 be arbitrary. We're gonna set, oh, okay, again, we're assuming the case that A is not 0. Okay, set epsilon2 to be epsilon over 2 times the absolute value of A. Okay, then I also want to pick epsilon1, but before I do that, I need to explain why capital M is. Because the limit of the bn's equals b, then the sequence bn is bounded. Assume that bn is less than or equal m. So that's the bound, capital M, right? So we're using the first theorem we proved today. Now, set epsilon1 to be epsilon over 2m. Good. Now, because the limit of an equals a, then, and here we're using epsilon1, there is capital N1 such that if little n is bigger than capital N1, then an minus a is less than epsilon1. And remember, epsilon1 is epsilon over 2m. Similarly, because the limit of the bn is b, then this time we're using epsilon2. There is n2 such that if little n is bigger than n2, then bn minus b is less than epsilon2, where epsilon2 is epsilon over 2 times the absolute value of a, right? And let's actually, I mean, when you start getting a lot of equalities and inequalities, etc., probably better to number them. So let's call this one 1 and this one 2. Okay. And now what? Well, now.
Question here.
Yes.
Didn't we define E1 as, isn't E1 associated with the B's? Or is it, I'm a little confused.
Yeah, let's go back to our,
yeah,
to our
why is that the case?
Yeah, so for E1, epsilon1 is because we want to control an minus a. But we want it so that when we multiply by bn, we get epsilon over 2, right? So for that, so yes, epsilon1 is for the a's, and it does involve the m, and the m comes from the b's.
Thank you, that helps.
Yes. Yeah, like I said, not as easy as before, right? We needed to, I mean, it's like, there's a creative process here, right? I don't want to instill to you the opinion that this is super easy or that you're gonna learn recipes for doing this. No, you need to come up with these ideas, right? Like how are we gonna control this? So, fine. So now what we need is to be able to use both 1 and 2. And so the same thing applies, right? To be able to use both 1 and 2, we're going to use the maximum of n1 and n2. So we're going to set n to be the maximum of n1 and n2. And choose some little n bigger than capital N. So in particular, i.e. n is bigger than n1 and n is bigger than n2. It's the little n should exceed both of them, which means I can use both 1 and 2. Okay, so then this happens. If I write bn minus ab, I can introduce the term we added, the tricky middle term, which is a times bn plus ABN. I didn't use a different color this time because I had used it before. Then by triangle inequality, this is ANBN minus ABN. And over here, ABN minus AB. Then by simplifying that expression, factoring what they have in common, that's the same as, so this is, I mean, I'm going to write less than or equal because I'm carrying the inequality here, but from here to here is actually equality. So I can factor the Bn, so that's An minus A times Bn plus A times Bn minus B, which is the same as if I separate this as the product of the corresponding absolute values. So that's An minus A times absolute value of Bn plus absolute value of A times absolute value of Bn minus B, right? Okay, now time to use my inequalities. Where do I use them? Well, let's see. So here I'm going to be using 1 and 2. So 1 and 2 are going to be used here, plus one extra piece of inequality, which is that the Bn is bounded. Remember, Bn is bounded? Let's go all the way over here to the top. We said that Bn is bounded by M. So we're going to use that one too. So right here, we're going to use that this one over here, An minus A, that one is smaller than epsilon 1. Bn is smaller than M. Capital A, we're going to leave the way it is. It's just a constant. And Bn minus B is bounded by epsilon 2. Let's see if I can make them fit. Oof, I can't. Okay, right there. So An minus A minus A is less than epsilon 1. That's the one we're using here. Bn is bounded by M. The A, we just leave it there. And this one is epsilon 2. Bn minus B is less than epsilon 2. And now where the magic happens, which is we already know what epsilon 1 stands for. Epsilon 1 starts for epsilon over 2m. Epsilon 2 stands for epsilon over 2 absolute value of A. Now things cancel the way we wanted them, so the A goes away, the M goes away, and this is epsilon over 2 plus epsilon over 2, which makes it epsilon. And we are done, right? So given an arbitrary epsilon, we picked a capital N that depended on N1 and N2. And if little n is bigger than capital N, then this difference is less than epsilon.
For the last line, do we want to have just a strictly less than or a less than or equal to?
At some point there should be strict, right? Where is the one here should be strict, right? Thank you. Yeah, you want one of them to be strict. And this one will be strict because one of these is, as long as these are strict, this one will be, right? Yeah, thank you. All right, and that's the end of that one. Okay, and we have one more. Okay, so again, we left a case pending here, which is what happens when A is 0. And I think, let me just quickly check, but I believe it may be one of your problems in the homework. Let me see if it's exactly written like that. Yes, it's exercise 2.3.9. So if A equals 0, do exercise 2.3.9. So you're supposed to be able to handle that case by yourselves, and I agree. Okay, so let's check the last one. So what about the last one? And for the last one, actually, if you think about it, we only need to do, so for 4, let me write 4, or recall what 4 was. No need to write it again. So let's put it here on the, so here's 4. We want to do the quotient. So instead of doing the quotient, I want to think of this as AN times 1 over BN. So if we already knew 1 over bn, we can conclude this one over here. All right, let me explain. So for 4, I'm gonna say that it is enough to show that if the limit of bn equals b and b is not 0, then the limit of 1 over bn is 1 over b. If we do that, we can do the other one. Why?
Because at that point, it just becomes proof number 3.
Exactly, it becomes a multiplication one, right? Because then if you want to do the limit of an over bn, you can write that as the limit of an times 1 over bn. Use property 3, and property 3 would tell you that this is the limit of an times the limit of 1 over bn. And now this is a, and that's 1 over b, and that's exactly a over b, right? So all we need to do is this one, right? So in that sense, it's like we already done some hard part of the work. So we're only left to do with something that it's considerably easier. So let's try to do this one instead. So the part that is just enough. So now how do we do this? Well, again, let's write out what we want. We want 1 over Vn minus 1 over b to be less than epsilon whenever n is bigger than capital N, right? So I didn't write everything this time. It's more precisely, we want given epsilon to find a capital N that makes this happen. We want given epsilon greater than 0, find capital N such that this beauty happens, right? And as usual, the way we want to proceed is to start with what we want, right? So let's try to simplify this, make sense of this. The one we know is that Vn minus b we can control, right? So let me put it here. We can control Bn minus b. Okay, I'm not going to write the definition again and everything. I'm just trying to streamline a little bit the way in which you think of the right way of doing the proof. Okay, so so from this one here, maybe we do the fraction. We find a common denominator. So this one over here becomes, what does it become? Bbn as the common denominator, and then in the top is b minus bn, right? And this makes me happy because I can see one of the parts that we want. The b minus bn part is there, right? So this is the same as b minus bn divided by b bn. Okay, now here again, we're going to have a little bit of a problem. See, because ideally we would like to use our, you know, we remember we call it epsilon-1 or epsilon-2, epsilon prime, and we would like to choose this number multiplied by this, but we don't know if in this case the bn is 0, right? In fact, bn, what if bn is 0 a lot of times? What if the sequence has a lot of zeros? That would be a problem because then we would be here dividing by 0, right? So we know the limit of the sequence is not 0. So can we then show that eventually there are numbers that are bigger than 0? That's what we would need, right? And we can do that indeed. Yes? So now the idea to control, so here we're almost happy. This part is we're really happy, no problem. The divided by b, no problem. The b over n, problem, right? This one over here, we need to control. And when I say we need to control, I say we need to check that it doesn't become too small. If it becomes too small, we're in trouble. So we need to say that it's always bigger than something, okay? And why do I say that we can do that? Well, because think about it. It's picture time. Here is a picture of the Bn sequence. We know it converges to B, and B is not 0. That's important, right? B is different from 0. Otherwise, the whole thing doesn't work. So because it's different from 0, I chose to put it on the right, but it could be on the left. It really is the same thing. Then you have the sequence, right? So here is the sequence. So you have B1, maybe B2, B3 here, maybe B4 goes farther, maybe B5 is 0, maybe B6 is 0. But eventually, they're going to be really, really close over here, right? To B. Okay? So because they're going to be really, really close to B, we can guarantee that eventually none of them are 0. How can we do that? Well, just pick an epsilon that is smaller than the distance from here to here, right? So pick epsilon 1. So whatever this distance is, oh, we know what that distance is. That distance is absolute value of B. Well, just pick your epsilon 1 to be smaller than that. If we pick an epsilon neighborhood around B, epsilon prime neighborhood around B, with epsilon prime smaller than absolute value of B, we avoid the zeros. And that's where the problem lies. Okay. Now, to make it more reasonable, we could probably pick half, right? So to make it, to give ourselves some room to work with, don't pick just absolute value of B, pick half this distance. All right, so let's pick in the definition of the sequence Bn. Okay, so let me write it down. The limit of Bn is B. What does that mean? It means that for any epsilon prime, there is capital N prime, such that if little n is bigger than n prime, then Bn minus B is less than epsilon prime. So pick epsilon prime to be like smaller than absolute value of B over 2. Choose epsilon prime smaller than absolute value of B over 2. That way we can guarantee that these Bn's are not 0, right? And if they're not 0, then we can control them right here. Okay? That's the idea. So we need to check that they're not 0. So we probably won't finish the rest of the proof today. So there's only one step that I want to take care of before we adjourn for the day, and which is to say, what is the lower bound that I can guarantee for Bn if this happens? So what is the lower bound for Vn in this case? That's what we want for absolute value of Vn, because it has absolute value bars, right? And then just like I was telling you the other day, the way you can do this is you start with what you want, and then you carry it around. Now, using the triangle inequality. Now, here it's a little bit trickier because we want, the triangle inequality works nicely if you have an upper bound. Here you want a little bit of a lower bound, so you need to sort of start from the other side. So here's the way to do it. See, look at the following. B is the same as B minus Bn plus Bn. Of course, right? I just added and subtracted. Then by the triangle inequality, this is B minus Bn plus Bn. Now this one we can control because it's less than epsilon prime. Yeah.
It's 146.
I know. I'm about to be done. That's what I said. But I just wanted to show you this lower bound before I adjourn. So give me 30 seconds. I'm about to finish this thought. So this Bn minus B is less than epsilon prime. And this epsilon prime is less than absolute value of B over 2. So this is less than absolute value of B over 2 plus absolute value of Bn. And then if you look at these two, what you get is that B minus B halves is less than Bn. And this happens to be absolute value of B over 2. And that's where we're going to pick it up next time. So I have a lower bound for the absolute value of Bn, which is magnitude of B over 2. And this is the inequality that we can use to control this term over here. All right? Good. So we'll finish the rest of the proof next time. And I'll see you guys next week.